What's going on, Algebra Bros? It's Mr. C here, and in this video we're going to discuss one of the most important results in many people's eyes of algebra. It's called the Fundamental Theorem of Algebra. So I hope to put the fun in fundamental instead of the mental in fundamental, but either way, that's what we're going to be discussing in this video. And to kind of motivate this topic, I'm going to write out a few polynomial functions along with their corresponding zeros. So one polynomial function I have in mind is f of x equals x squared plus 5x plus 4. The zeros for this polynomial function would be -1 and -4. Right, and that's because this function factors as x plus 4 times x plus 1, and if you set each factor equal to 0 to solve for x, you would get these as your answers. Another polynomial function I want to include is a degree 3 polynomial function, f of x equals x cubed plus 7x minus 6x, 7x squared minus 6x minus 42. The zeros for this polynomial function are -7, positive radical 6, and negative radical 6. Another polynomial function that I want to include is another degree 3 one. This time it's going to be 2x cubed minus 5x squared minus 4x plus 12. And I'll go ahead and provide its zeros. Its zeros are 2, and 2 again, and -3 over 2. One thing that I hope you're noticing with each of these polynomial functions and its corresponding zeros is that the total number of zeros is equal to the degree of the polynomial function. So for instance, with f of x equals x squared plus 5x plus 4, the degree is 2, and there are 2 zeros. With the second polynomial function, it's a degree 3, and there are 3 zeros. If you look at the third polynomial function, there are 3 zeros, but only 2 unique ones. So if you include the multiplicity of the 0 of 2, then that last polynomial function has 3 zeros, in which case one of them has a multiplicity of 2. So this is actually no accident. It was proven, I believe, a couple hundred years ago that every polynomial function has exactly n zeros. And by this n, I mean the degree of the polynomial function. So if it's a degree 2 polynomial function, there are going to be 2 zeros. A degree 3 polynomial function is going to be 3 zeros, and so on and so forth. But there is sort of this asterisk statement that comes along with it. It doesn't mean that a polynomial function's zeros are all going to be completely different, and they're all going to add up to n. There are some cases where that's the truth, but this is assuming, or this wants you to assume that there are those possibilities where a polynomial function is going to have zeros with multiplicity larger than 1, or even polynomial functions that have imaginary solutions. So we're actually going to see an example of that in this section. So the little note here says the n in the above result takes into account zeros that are real, zeros that are non-real, so those are the ones that have i's, and zeros that repeat. So what that means is zeros that have a multiplicity that's greater than 1. So if you are basically all-inclusive with the types of numbers you get as zeros and their repeats, if any, then the total number of zeros the polynomial function should have is equal to the degree. Now, this gives way to what's called the linear factor theorem. Keep in mind that once we find the zeros of a polynomial function, we're able to factor the polynomial function. And one way that we can factor it is by using a zero factor table. And if I just pick on one of the polynomials from above, maybe the first one that's quadratic, x squared plus 5x plus 4, we notice that its zeros are -1 and -4, and we can use the following formula to create its factors, x minus the 0. So if -1 is a 0 of that polynomial function, then one of the factors is going to be x minus -1, or simply x plus 1, and the other factor is going to be x plus 4. Again, the plus sign is due to the double negative. And this would help us factor that polynomial function, and it would factor as x plus 1 times x plus 4. So because every 0 can be used to create a factor of the polynomial function, then since a polynomial function is going to have exactly n zeros, then the factored form of the polynomial function is going to have exactly n linear factors. So for instance, x plus 1 is a linear factor and x plus 4 is a linear factor, and there are two of these linear factors because there were two zeros. So if we had included 3 zeros in the table, we'd be working with a degree 3 polynomial function, and you would see that it factors into 3 linear factors. One more thing before I cut the video here, and in order to create another one for the rest of it, there's something called the Conjugate Pairs Theorem, and this is kind of a little neat result. Basically it says that anytime that you get zeros that include the imaginary unit I, they're going to come in conjugate pairs. Specifically, if a plus bi is a 0 of the function f of x, then so is its conjugate a minus bi. So let's take a look at a quick example, something like this. Let's say that we had the function f of x equals x squared plus 25, and we wanted to find its zeros. Then that requires us setting the polynomial equal to 0 and solving for x. So that'd be x squared plus 25 equals 0. If you bounce the 25 over to the right-hand side, we get x squared equals -25. And taking the plus or minus square root of the right-hand side, we get two answers for x, positive and negative 5i. So there are two zeros, as we would suspect, because this polynomial function has a degree of 2. Both of the zeros are non-real, they include i's. One of the zeros is 5i, and the other 0 is -5i. And those two answers for x look very similar to each other, don't they? But obviously one is the opposite of the other. Well, the idea here is that, because these are non-real zeros, they're going to come in conjugate pairs. 5i and -5i happen to be conjugates of each other. So one implication of this conjugate pairs theorem is that if you get a 0, say it's 1 plus 2i, like you're seeing in this example towards the bottom of the screen here, it's never going to show up as like a lone 0. It won't just be a single 0 in and of its own right, and there be nothing else associated with it. If 1 plus 2i is a 0 of the polynomial function, then it has to be the case that there's a second 0, and that second 0 would be its conjugate 1 minus 2i. So hopefully that's all making sense. Of course, if you have any questions about this video or anything discussed in it, feel free to let me know. Otherwise, thank you for watching, and I will catch you in the next one.